In general solution, the solution contains an arbitrary constant, whereas particular solution is free from any arbitrary constant. The differential equation is xy d square y by dx square plus x into dy by dx whole square minus y into dy by dx is equal to 0. If the axis is along the positive direction of x-axis, then it is clearly a right-handed parabola whose equation is y square is equal to 4ax. Hello everyone, a warm welcome to one and all. This is Yashati ma'am lecturing in Vidhyaashram, the Temple of Excellence, Mysuru. So in this session, we are going to study about the formation of differential equation whenever its solutions is given. So in the previous session, we have learnt what is differential equations, order and degree of differential equation, and whether the given function is a solution for the given differential equation or not. But here, we are going to form the differential equation whenever the function is given. So, how to form a differential equation whenever its solution is given? So, formation of differential equation whose general solutions are given. So, I already said you we have two types of solution. One is general solution and another one is particular solution. In general solution, the solution contains an arbitrary constant, whereas particular solution is free from any arbitrary constant. So, to form a differential equation, the general solutions are necessary. So, now here to form a differential equation of a given function, we differentiated. How many times? We differentiated. But how many times? Until all the arbitrary constant vanishes. Suppose if you have one constant, until that constant vanishes, we are going to differentiate the entire equations again and again, and then we will form a differential equation. So, let's take an example. Now, I have y is equal to e power 3x plus e power minus 2x. So, let me take two arbitrary constant a and b. So, thus the equation becomes y is equal to a into e power 3x plus b into e power minus 2x. Now, here, so let me derive this. Then it is y dash. Y dash is equal to a e power 3x can be written as 3 times e power 3x plus b minus 2 e power minus 2x. So, now here then y dash becomes 3a e power 3x minus 2b e power minus 2x. Let me differentiate this again. Then it is y double dash is equal to, so this becomes 3a 3 e power 3x minus 2b is already there here. So, it is again minus 2 e power minus 2x. So, let me take an example of y is equal to a e power 3x plus b e power minus 2x. So, let me differentiate it. We have two arbitrary constant here. One is a, another one is b. We have to eliminate it. To eliminate it, what are the sorts of purpose we can do? We will do it for simplification. So, let us differentiate it. Y becomes y dash, that is dy by dx. We are differentiating with respect to x. So, the first one become a. We know the derivative of e power ax is a into e power ax. So, this becomes 3 into e power 3x. Next we have plus, here we have minus 2 e power minus 2x. So, next I have y dash is equal to 3a e power 3x minus 2b e power minus 2x. So, what I will do here, I will take y dash as 3a e power minus 3x plus 3b e power minus 2x minus 5b e power minus 2x. So, for this, I will take this as a sum of plus 3 and minus 5, which is one and the same. Now, for the first one, first two terms here, I can take 3 as a common factor. If you take 3 as a common factor, you will get a into e power 3x plus b into e power minus 2x minus 5b e power minus 2x. Clearly, you see, this is nothing but our y. So, replace it with y. Then we get y dash is equal to 3y minus 5b e power minus 2x. Now let us differentiate it again. If you differentiate dy by dx, it becomes d square y by dx square. That is nothing but y double dash. So y double dash is equal to, now derivative of y is dy by dx. So therefore 3 into y dash I can take. Next I have minus, so this is again 5 minus 2b e power minus 2x. So here we have y double dash is equal to 3y dash plus, this becomes 10b e power minus 2x. So I'll write 10y double dash is equal to 3y dash, as I'll take 2 as a common factor and I'll take 5b e power minus 2x. See, here if we want 5b e to the power minus 2x, I can shift this here and shift this here. Let me take this as equation 1. So before differentiating, let me take this as equation 1. Now, there I need 5b e power minus 2x. So from equation 1, I can rearrange. If I want 5b e power minus 2x, I can write it as 3y minus y dash. So therefore here, y double dash 3y dash plus 2 into, so what happens? This becomes 3y minus y dash. So 3y minus y dash. So now it is y double dash 3y dash 6y minus 2y dash. So y double dash is equal to 3 minus 2 becomes y dash plus 6y. So now let's shift all towards one equation. So it is y double dash minus y dash minus 6y is equal to 0. Thus this is the required differential equation. See here, it is all in the polynomial form. So y double dash means d square y by dx square. Y dash is nothing but dy by dx, and y is the given function. Thus the solution can be expressed in terms of a differential equation. Now let's form the differential equations of a given general solution. Form the differential equation representing the family of curves y is equal to mx, where m is arbitrary constant. So we have a function y is equal to mx. Differentiated, it is dy by dx is equal to m. Now let me take this as equation 1. Substitute m is equal to dy by dx here. Then it becomes equation 1 implies y is equal to dy by dx, and here we have x, or when you shift it, you can write it as x into dy by dx minus y is equal to 0. So this is the differential equation of the solution y is equal to mx. Next question, form the differential equation representing the family of curves y is equal to a sine of x plus b, where a, b are arbitrary constant. So previous problem, we have one arbitrary constant, we have substituted it at m is equal to dy by dx, and hence we got the differential equation. And here we have two arbitrary constant, one is a, another one is b, we have to eliminate it. So we have y is equal to a sine x plus b. Let us derive it. Then it is dy by dx is equal to a is constant, sin ax plus b becomes cos x plus b. Now again differentiate it, then it is d square y by dx square, a is constant, derivative of cos is minus sin x plus b. See here, a sin of x plus b is nothing but y, replace it. So it is d square y by dx square is equal to minus y, or d square y by dx square plus y is equal to 0. So this is the differential equation required. Next question, form the differential equation representing the family of curves y is equal to e power x, a cos x plus b sin x, where a, b are arbitrary constant. So here we have y and e power x. Let me shift e power x to the left hand side. So then this becomes y into e power minus x. So on the right hand side you have now a cos x plus b sin x. Now let us differentiate with respect to x now. So here we have two functions, one is y, another one is e power minus x. Let me derive it. So first function into derivative of the second, that is minus e minus x plus second function into derivative of the first, that is I'll write it as y dash. Y dash represent dy by dx because derivative of y is dy by dx. I'll write it as y dash. Now here it becomes minus a sin x plus b cos x. So now next, let us differentiate it again. Then here again apply the product rule here. So first function, already we have minus here. So derivative of the second is again minus into minus plus e power minus x. Plus again we have minus e power minus x into y dash. Next here apply the same thing. So first function into derivative of the second is y double dash plus second function y dash into derivative of the first is minus e power minus x. On the right hand side it is again minus a cos x minus b sin x. Now here we can see y e power minus x minus e power minus x y dash plus e power minus x y double dash, and here we have minus e power minus x y dash is equal to, if I take minus as a common factor, it is a cos x plus b sin x, which can be written as y divided by e power x, or we can write a cos x plus b sin x as y into e power minus x. Now let me multiply e power x throughout the equation. If you multiply e power x throughout the equation, e power minus x, e power x becomes e power 0 whose value is 1. So here it becomes y minus y dash plus y double dash minus y dash is equal to minus y. So rearrange this, we get y double dash, we have minus y dash minus 2y dash. Already we have y here, and addition of one more y plus 2y is equal to 0. So this is the differential equation required. Next question. Form the differential equation representing the family of curves x by a plus y by b is equal to 1. So we have an implicit form of a function, that is x by a plus y by b is equal to 1. Let us differentiate. Derivative of x is 1 and 1 by a is constant. Let me write it. Derivative of y can be written as y dash by b. Here it is 0. Now differentiate it again. So second derivative. What is derivative of 1 by a? It is 0. And here what is derivative of y dash? It is y double dash divided by b we have is equal to 0. So when you take b there, it is y double dash is equal to 0. So what is y double dash? It is nothing but d square y by dx square is equal to 0. Hence this is the differential equation required. Next question. Form the differential equation representing the family of ellipses having foci on x-axis and center at the origin. We know that they have clearly given the foci is on x-axis and center it as origin. So if we consider two focuses for an ellipse, this represents the ellipse. So we are now finding the differential equation for the family of this ellipse whose focus are on the x-axis and center is at origin. So what is the standard equation of ellipse whose focus lies on the x-axis? It is x square by a square plus y square by b square is equal to 1. So this is the standard equation of an ellipse. So here let us differentiate it. So 1 by a square is constant and x square is 2x. So derivative of x square is 2x by a square. Next y square can be written as 2y by b square into dy by dx is equal to 0. So therefore here you can clearly say, let's see what is dy by dx now. So dy by dx is equal to minus 2x by a square into b square by 2y. So 2 get cancels. We can write it as minus b square by a square, and here we have x by y. So this is dy by dx. Now here let me differentiate this again. So if you differentiate this again, you will get d square y by dx square Here I can take minus b square by a square as a common factor. So let me derive x, y. So here what happens? So y into 1 minus x into dy by dx divided by y square. So next question. Form the differential equation representing the family of ellipses having foci on x-axis and center at the origin. So having foci on x-axis is nothing but the major axis is the x-axis and center lies at the origin. So here we are going to find the standard differential equation for this family of circles. So whose focus lies on the x-axis. Now here what is the standard equation of this type? It is given as x square by a square plus y square by b square is equal to 1. Now let us go on differentiating. Derivative of x square is 2x and 1 by a square is a constant. Derivative of y square is 2y and here we have b square. Along with that we need to write dy by dx because y with respect to x we are taking, so it is 0. So now we have here 2y b square dy by dx is equal to minus 2x by a square. I'll cancel 2 on both sides. I'll shift b square and x here. Then it becomes y by x dy by dx is equal to minus b square by a square. Let me take this as equation 1. Now differentiate this equation again. So take this as one function, dy by dx as another function. Apply the product rule. So first function y by x into derivative of second is d square y by dx square plus dy by dx into derivative of this. So since this is in the quotient form, apply this rule. So x into dy by dx minus y into 1 whole divided by x square. And on the right hand side you have minus b square by a square which is a constant. So therefore it is 0. Now here we have y by x d square y by dx square plus dy by dx. And here we have x into dy by dx minus y whole divided by x square is equal to 0. So multiply x square throughout the equation. Then here it becomes x y d square y by dx square plus x into dy by dx whole square, because dy by dx 2 times which becomes whole square, minus y into dy by dx is equal to 0. So this will be the standard differential equation for an ellipse whose foci lies on x-axis and center at the origin. Next question. Form the differential equation of the family of ellipses having foci on y-axis and center at the origin. So here we are taking the family of ellipses whose major axis will be along y-axis and minor axis will be along x-axis. Here also you can take the standard equation of the form x square by a square plus y square by b square is equal to 1. Here b is greater than a. Previously a was greater than b. So therefore for the same equation what we have done, the same thing we will get here. So the answer will be xy d square y by dx square plus x into dy by dx whole square minus y into dy by dx is equal to 0. So again for this type of ellipse also the differential equation is xy d square y by dx square plus x into dy by dx whole square minus y into dy by dx is equal to 0. Now form the differential equation of the family of circles touching the y-axis at origin. So what is the general equation of a circle touching the origin? So here we are going to find out this family of circles like this. So this circle touches on at the origin. So what is the general equation of this type of circle? It is x minus a whole square plus y square is equal to r square. So r is nothing but the radius of the circle, or in general we can write this as x square plus y square is equal to 2ax. So let me take this as a standard equation. So this is the standard equation of the family of circle touching the y-axis at origin. Similarly, we can write the standard equation of a circle x square plus y square is equal to 2ay touching the x-axis at origin. So these circles we can take. So the circles of this form. So these circles touch the origin along x-axis. Now using this standard equation, we can form a differential equation. Now the question is form the differential equation to the family of circle which touches y-axis at origin. So the general equation is here. Now let us differentiate it. So we have 2x plus 2y into dy by dx is equal to 2a. So we can cancel 2 on both sides. Then the equation becomes x plus y dy by dx is equal to a. So let me take it as equation 2. Let us differentiate it again. Derivative of x is 1. So here we have to apply the product rule. First function into derivative of dy by dx is d square y by dx square plus second function is dy by dx and derivative of y is also dy by dx. And here the constant is 0. So clearly you can see this is y into d square y by dx square plus dy by dx whole square, because it is repeated 2 times, plus 1 is equal to 0. Now let me take this as equation 2. So in the place of 2a, then equation 1 implies here x square plus y square is equal to, in the place of 2a, we are going to write 2x plus 2y into dy by dx. Outside we have x. So let us multiply x square plus y square is equal to 2x into x is 2x square, and here we have 2xy dy by dx. So on the left hand side we have x square. So when you shift it, when you subtract it, 2x square minus x square is x square, plus y square when you write it becomes minus y square, and here we have plus 2xy dy by dx is equal to 0. So thus this is the required differential equation of the family of circles touching y-axis at origin. Next, form the differential equation of the family of hyperbolas having foci on x-axis and center at origin. So hyperbola, clearly they have said the focus is on x-axis. So therefore the transverse axis will be like this. So this is your hyperbola. So focus somewhere here and the center at the origin. So what is the standard equation of this? That is x square by a square minus y square by b square is equal to 1. So let me differentiate this. Then it is 2x by a square minus 2y by b square dy by dx is equal to 0. On solving we get dy by dx, and here we can shift to the positive side. Then it becomes b square by a square here and y by x here. So if you shift towards that side, then we can cancel 2, 1, 2. So then if you shift b square to the numerator, then x comes to the denominator. Now again differentiate it. So we have two functions here. First function into derivative of second, that is d square y by dx square, plus second function, that is dy by dx, derivative of first, apply the quotient rule. So let me write dy by dx minus y, derivative of x is 1 whole divided by x square is equal to, we have a constant here, so it is 0. Now here multiplying x square towards the equation, we get x y d square y by dx square plus. So when you can multiply x square, it get cancels. So x into dy by dx whole square minus y into dy by dx is equal to 0. So this is the require differential equation for the family of hyperbolas whose focus lie on x-axis and center at the origin. Next question. Form the differential equation of the family of parabolas having vertex at origin and axis along positive direction of x-axis. So, if the axis is along the positive direction of x-axis, then it is clearly a right-handed parabola whose equation is y square is equal to 4ax. Now, let us derive it. Then it is 2y dy by dx is equal to 4a. Let me take this as equation 1 and let me take this as equation 2. Put 2 in 1. Then equation 1 implies y square is equal to, instead of 4a, we can write it as 2y dy by dx into x. Or we can write it as y square minus 2xy dy by dx is equal to 0. So, just eliminating the arbitrary constant, we can form a differential equation. Next question. Form the differential equation of the family of circles having center on the y-axis and radius 3 units. So, if the equation has center on y-axis, then the general equation can be written as x square plus y minus k whole square is equal to r square. So, the radius is given as 3 here. So, it becomes 3 square which is equal to 9. Now, differentiating this equation, we get here 2x and here we can write it as 2 into y minus k dy by dx is equal to 0. Next, we can divide the equation with respect to 2, then it becomes x plus y minus k into dy by dx is equal to 0. Next, this becomes y minus k dy by dx is equal to minus x, or I can write y minus k is equal to minus of x dy by dx. So, now again differentiating with respect to x, if you differentiate it y, it is dy by dx minus, if you differentiate k, it is 0. Here outside we have minus. So, we have two functions here, one is x, another one is dy by dx. Let us apply the quotient rule. So, dy by dx into differentiation of 1 minus x into derivative of dy by dx is d square y by dx square whole divided by dy by dx whole square. Now, here when you multiply here, this becomes dy by dx whole cube is equal to minus dy by dx minus x into d square y by dx square. So, now I can write here y minus k is equal to minus x divided by dy by dx. Now, let me take this as equation 2. So, look at equation 1. Let me replace y minus k by x divided by dy by dx whole square. Then the equation 1 implies x square plus minus x divided by dy by dx whole square is equal to 9. So, clearly you can see this is equal to 9. So, then this is x square plus x square divided by dy by dx whole square is equal to 9. Now, multiply this. So, here dy by dx whole square, if you multiply, then it is x square dy by dx whole square plus x square is equal to 9 into dy by dx whole square. So, take x square as a common factor, then x square is dy by dx whole square plus 1 is equal to 9 into dy by dx whole square. Or we can also write this in another form, that is x square y dash whole square plus 1 is equal to 9 y dash whole square. So, this is the differential equation required for the family of circles having the center on y axis and radius is 3 units. So this is how we are going to form the differential equation whenever the general solution is given or the general equation is given of certain family of curves. So these questions may be asked for 3 marks in your examination, which is very important. That is, formation of a differential equation can be asked for 3 marks in your examination. We'll meet you in the next session with a new concept. Until then, keep watching, keep learning, keep exploring. Thank you.